Hey guys, welcome back to the Spacecraft Design and Engineering course provided by Astroden. I'm Shushanth, and I'm going to be instructor for lecture number 2 of this series. Okay, so what are our objectives for today's lecture? First, we're going to go over the basic physical principles that govern how a rocket functions. Then we're going to go over tsiolkovsky's rocket equation and the phenomenon known as the tyranny of the rocket equation. Then we're going to go into the demonstrations of the principles by using Kerbal Space Program simulations of these concepts. So first up, we have Newton's third law, probably the most basic and most fundamental physical principle behind how rockets function. So Newton's third law states that for every action, there's an equal and opposite reaction. So in the case of a rocket, the action would be the exhaust gases being pushed out of the engine nozzle through a chemical reaction, and the reaction of this is that the exhaust exerts an equal and opposite force on the rocket itself. And so this is a fundamental part of propulsion technology, and I cannot stress this enough. So next we're going to look at reaction control thrusters as an example for how Newton's third law is put into practice. So most spacecraft utilize these things called RCS thrusters, which are small thrusters utilized to navigate while in space. These small engines apply thrust in certain directions and certain orientations in order to control the rotation and translation of a spacecraft. Now let's look at a demo of Newton's third law in actual principle. So right here we have a sample spacecraft that has 4 sets of these RCS thrusters that are located on all sides of the spacecraft, as well as the thrusters on the capsule itself. So this right here is what happens when I activate thrusters in this fashion that I'll show you right now. So as you can see, these thrusters are all applying a force based on, once again, Newton's third law principle, in that the exhaust gases are the reaction in this system. And the exhaust gas pushing back on the spacecraft, that is. And what this causes is the whole spacecraft to rotate around a central axis, because these forces are being applied perpendicular to the central axis, meaning that they apply a direct torque that's proportional to the force, right? So that's how this whole system works. And we can also use this for translational control in real spacecraft. So, for example, if I want to move the spacecraft closer to this other target right here, as you can see, the thrusters are experiencing a force from the exhaust gases. The exhaust gases are being pushed out. So here's another action-reaction pair being utilized for translational movement as well. So this is the basis of how most orbital spacecraft work. They utilize these thrusters for rendezvous purposes, for fine adjustments, and so yeah, it's a very interesting example, and I wanted to show it off to you guys. So yeah. Next, we'll get into tsiolkovsky's rocket equation, which describes the amount of delta V a rocket or a space vehicle has. So delta V, what does it mean? It means the change in velocity of the vehicle, so the final velocity minus the initial velocity. VE means the velocity of the exhaust of the byproducts of the vehicle produced during the chemical reaction and combustion. The MO right here, this MO term, is the full mass of the spacecraft. So that includes the dry mass, which is just the mass of the spacecraft without the fuel, combined with the mass of the fuel itself. And the final mass is typically the dry mass, so the mass of the rocket excluding the fuel that was expended. Now we'll look at what factors affect delta V. So first of all, the most obvious one, exhaust velocity. So a higher exhaust velocity is going to contribute to a higher delta V because it's directly proportional to delta V. And so this can be obtained by utilizing exhaust byproducts that have less mass. So for example, having an exhaust byproduct like hydrogen, for example, the lightest molecule would increase delta V, and also having molecules like water vapor would also help when compared to things like carbon dioxide, etc. Another factor could be increasing the energy of combustion, which would also contribute to an increased exhaust velocity. And let's look at what VE itself means. So the exhaust velocity is equal to the specific impulse of an engine, which is kind of like the gas mileage of like a car. It's the same thing, but for an engine, times a gravitational parameter. In most cases, we're going to be using 9.8 meters per second squared. And so increasing specific impulse, since that is proportional to the exhaust velocity, which is in turn proportional to delta V, by increasing that, we can also increase delta V. And the other part is increasing the other part of the equation, right? The natural log of the mass ratio. So increasing the ratio of fully fueled mass to dry mass would positively affect delta V. But the one thing we have to make sure to notice is that because it's a natural log function, as the limit approaches infinity, the function begins having smaller and smaller increments for increasing, right? So it's not linearly related. So that's something important to pick up for another demo we're going to be doing shortly. Okay, so now moving on to the tyranny of the rocket equation phenomenon. So let's go into a few terms, right? So the thrust to weight ratio, or TWR. This is the ratio of the force applied by the thrust of the engines to the total weight of the rocket on launch. And most rockets have a TWR of about 1.2 to 1. And if it's below 1 to 1, the rocket will not take off. It won't even leave the pad. So adding fueled mass, so the tyranny of the rocket equation, essentially what it means is that by adding fuel mass, we can increase delta V because we're going to add to the mass ratio. However, by doing so, you also decrease the thrust to weight ratio because the whole rocket weighs more. So at some point, there's a trade-off where the TWR will drop faster than the delta V that is gained by adding fuel to the rocket, since the mass ratio is a natural log function, while the thrust to weight ratio isn't. And so right here to the left side, we have a graph. So this is modified for another celestial body, but just as reference, we can see that this function starts to taper off as we add more and more fuel as well. So there's another aspect to it. The marginal increases to the natural log function will definitely be surpassed by the decrease in TWR in the future. To demonstrate Tsiolkovsky's rocket equation, I developed a small little rocket right here. It has one command capsule, a fuel tank, and an engine, and we're going to take it for a launch and see what happens. So right now, the spacecraft at sea level has 22,373 meters per second in total for delta V. And one other thing we got to pay attention to is the relative thrust to weight ratio. We got to see how fast the rocket essentially gets off the pad. A high thrust to weight ratio means the rocket is going to have a much higher net force upwards. So let's observe that right now with the space rocket. As you can see, the rocket jumped off the pad, a relatively high thrust to weight ratio, and it works just fine. So what if I want to improve the performance of this rocket by twice, right? What if I want to increase the delta V 2 times? Well, let's try adding fuel tanks and see what happens. So remember, according to Tsiolkovsky's rocket equation, the ratio of the total mass of the vehicle on launch to the final mass when it's empty of fuel follows a logarithmic function, right? So that means that as the function approaches infinity, it starts increasing at a slower and slower rate. So let's keep that in mind when we look at this delta V number right here. Let's change it up real quick. Okay, so this delta V number tells us that we have 3317 meters per second. Let's look at what we had before. 2423. That did not double our delta V increase. Instead, it basically added about 900 meters per second. That's not quite what we needed for performance improvement. But let's see what happens if we keep adding some more and more fuel tanks, right? Let's keep adding some until our delta V number increases substantially, right? Right now we're at 5,018. That's basically about twice, right? Well, it's going to drop because when we have the capsule on top. But that's about twice the initial delta V we had. So let's see how this rocket performs. 1 second. We just got to get a crew member on board. Okay. So let's test out this system right here. And see what happens. So, yep, we got 4,632 meters per second right here on the pad. And let's see what happens if we launch. 3, 2, 1. 1 second. And launch. Well, the rocket literally just fell back onto the pad. So what does this tell us? This tells us that the thrust to weight ratio now is literally less than 1. So the rocket has a lot more delta V in practice. Well, in principle, but in actual practice, when you look at the rocket, it can't even get off the pad. So this is the tyranny of the rocket equation. This is diminishing returns with adding fuel mass. The last physical concept regarding rocketry I want to get into is conservation of momentum. So what do we know about momentum? Momentum is equal to the mass times the velocity. So the conservation momentum states that if no net external force is applied to a system, in this case the rocket exhaust gases, the momentum of the rocket is conserved. And so what would be the initial momentum if rocket isn't moving at all? It would be 0 because the velocity is 0. And once all the fuel is expended, we get 2 different objects, essentially. So we're considering all the exhaust gases to be one object. So we have the rocket, which has m1, v1 of velocity in certain direction. We have the exhaust gases, which are in m2, v2. And thus, that means that m1, v1 has to equal negative m2, v2, since the exhaust gas and the rocket are moving in opposite directions, assuming no external forces are applied on the system. So that basically sums it up for all the physical concepts I want to go over in this lecture. So in the next lecture, we're going to go into the inner workings of propulsion technologies and how they might apply to the physics referenced in this lecture. And so we will look at different engine cycle types. But specifically, we're going to go into pressure-fed engines at first. In lecture number 4, we'll go into the more complex cycles. So yes, thank you for listening, and see you next time.